Hello and welcome to Sleepy Science. Tonight we discuss that, can you hear a black hole? The truth about sound in space, a sleepy science story, so let's start. The silent symphony of the cosmos. You float in the infinite dark, where stars sing a song you cannot hear. Space is not empty, it thrums with vibrations, but they dance in silence. Why does the universe withhold its music from our ears? You close your eyes, and for a moment, you imagine yourself untethered, not standing, not sitting, but suspended in the velvet blackness between worlds. Around you, the cosmos breathes. Nebulae exhale clouds of stardust, galaxies turn in their slow, graceful waltz, and somewhere in the distance, a star collapses in on itself with unimaginable force. Yet all of this happens in perfect, unbroken silence. This silence is not what you expect. On Earth, even the quietest moments hum with subtle sound, the rustle of leaves, the distant murmur of traffic, the rhythmic thump of your own heartbeat. But here, in the imagined void of space, there is nothing. No echo. No reverberation. Just an endless, weightless hush. Why? The answer lies in the nature of sound itself. Sound is not an object, not a thing you can hold. It is a traveler, a vibration that moves through the world by nudging molecules together, creating ripples in the air like waves across a pond. When someone speaks, their vocal cords tremble, pushing air molecules into a chain reaction that eventually reaches your ear. When a tree falls in the forest, its crash sends pulses through the atmosphere, shaking the invisible sea of nitrogen and oxygen that surrounds us. But space, true, interplanetary space, is not like Earth's atmosphere. It is not a sea. It is a desert. A vast, sprawling expanse where atoms are so few and far between that they might as well be lonely travelers crossing an endless plain. There is no medium for sound to move through, no molecules to pass the vibration along. If you were to scream in space, your voice would vanish the moment it left your lips, not because it was muffled, but because there was nothing to carry it forward. No air to tremble. No particles to dance. This is why the cosmos is silent to our ears. Not because it is still, but because it speaks in a way we cannot naturally perceive. And yet, if you listen differently, the universe is anything but quiet. Consider the sun, that great, glowing sphere that lights our days. To human ears, it is mute. But if you could stretch your senses beyond the limits of sound, you would discover that it is singing. The sun's surface ripples with waves, massive vibrations caused by the churning of superheated plasma deep within its core. These waves travel through the star like seismic tremors through the earth, rising and falling in slow, rhythmic pulses. Scientists call this helioseismology, the study of the sun's quakes, its hidden music. Or think of black holes. When two of these cosmic giants spiral toward one another, locked in a gravitational embrace, they do not crash with a thunderous boom. Instead, they send out ripples in the very fabric of spacetime, gravitational waves. These waves stretch and compress the universe itself as they pass, a silent vibration that human technology can now detect. In 2015, the LIGO Observatory recorded the collision of two black holes over 1 billion light-years away, not by hearing them, but by feeling the subtle warping of reality they left behind. Even planets have voices, if you know how to listen. Jupiter's magnetic field crackles with radio waves, a static hiss born from the interaction between the planet's atmosphere and the solar wind. Saturn's rings, those delicate bands of ice and dust, emit their own strange radio frequencies, a whisper of particles moving in unison. Scientists can translate these signals into sounds we can hear, turning the planets into ghostly choirs, singing in wavelengths just beyond our natural reach. So the universe is not silent. It is only waiting for us to learn its language. You let this thought settle over you like a blanket. The silence of space is not an emptiness, not a void. It is a different kind of fullness, a symphony played in a key we are only beginning to understand. And as you drift deeper into the quiet, you begin to wonder. If sound cannot travel in space, then what is sound, really? Is it only what our ears can detect, or is it something more? Something that exists beyond vibration, beyond air, beyond the limits of our perception? The answer, like the cosmos itself, is vast. And it begins not with a bang, not with a shout, but with a whisper. Or the lack of one. And so, you begin to wonder, what is sound, really? If it cannot exist in space, then perhaps it is not what you thought it was. Perhaps it is not a thing at all, but a traveler in need of a path, a wave without an ocean. What is sound, really? A wave without an ocean. Sound is a traveler, a ripple searching for a shore. But in space, there is no air to carry its footsteps, no medium to hold its hand. You learn how sound needs molecules like a dancer needs a floor. And yet, the cosmos finds other ways to sing. Imagine, for a moment, that you are a ripple on the surface of a still pond. You exist because something disturbed the water, perhaps a falling leaf, a skipping stone, or the gentle dip of a swan's beak. You spread outward in perfect circles, your energy passing from one water molecule to the next in an endless chain. This is how sound moves through the world, not as an object, but as a relationship between particles, a conversation passed from neighbor to neighbor. Now imagine trying to ripple across a desert. The sand stretches endlessly in all directions, but there is no water to connect one grain to another. Your energy would vanish the moment it began, with nothing to sustain it, nothing to carry it forward. This is why sound cannot travel through space, not because space is empty, but because its particles are too few and far between to whisper secrets to one another. On Earth, sound moves through air like a crowd doing the wave in a stadium. Each air molecule bumps into its neighbor, transferring energy in a chain reaction that eventually reaches your ear. The speed of sound depends on how tightly packed these molecules are, which is why sound travels faster through water, where molecules are closer together, and even faster through steel, where atoms are locked in a rigid embrace. But in the near-perfect vacuum of space, where a single atom might travel miles before encountering another, there is no crowd to do the wave. The cosmic stadium is empty. Yet this realization leads to a deeper question: if sound is just vibrating matter, then what happens when matter vibrates in ways we can't hear? Its surface seethes with convection currents, massive rivers of plasma rising and falling in cycles that last minutes or hours. These movements generate pressure waves, sound waves, technically, but they move through a medium so different from our air that they might as well be from another universe. The lowest frequencies, called P modes, resonate through the sun's interior like the deep notes of a pipe organ, some with periods of nearly 5 minutes. If you could stand on the sun's surface, an impossible thought, these vibrations would pass through your body at frequencies too low for human ears to detect. The sun isn't silent, we're just deaf to its particular music. The same principle applies to planets. Jupiter's magnetosphere crackles with radio emissions created by charged particles spiraling along magnetic field lines. When NASA's Juno spacecraft recorded these emissions and shifted them into the audible range, the result was an eerie chorus of whistles and pops, the voice of a world singing in plasma rather than air. Saturn takes this concept even further. Its immense rings, composed of countless ice particles, generate strange radio signals as they interact with the field. Converted to sound, these emissions resemble the haunting tones of a theremin, as if the rings were running ghostly fingers along the edges of reality. Even the emptiness between galaxies has a kind of sound, if we redefine what sound means. When two supermassive black holes merge, an event so powerful it shakes the fabric of spacetime, they produce gravitational waves. These are not sound waves in the traditional sense, but they share the same fundamental nature, rhythmic distortions moving outward from a source. The black hole merger detected by LIGO in 2015, when converted to audio, produced a distinctive chirp, a rising tone that lasted just fractions of a second, yet carried more energy than all the stars in the visible universe combined. It was the universe playing its deepest note on the instrument of spacetime itself. Perhaps the most profound implication is this: the distinction between sound and not sound may say more about our limited perception than about the universe itself. Bats navigate using ultrasound, elephants communicate with infrasound, and certain deep-sea fish perceive vibrations through their lateral lines, each creature inhabiting its own acoustic reality. The cosmos operates on scales both vastly larger and smaller than our middle-range senses can appreciate. What we call silence is often just the absence of vibrations in the narrow slice of reality our biology evolved to monitor. As you ponder this, your breathing slows, matching the rhythm of these cosmic vibrations. The room around you feels different now, not just as empty space, but as a medium humming with potential. Every surface, every molecule could carry vibrations if something set them in motion. And beyond your walls, the universe continues its grand performance, playing instruments we're only beginning to understand. This realization lingers as you drift toward sleep. If the quiet of space is an illusion, then so too might be the silence of destruction. Somewhere in dark, stars end their lives in cataclysms that should shake the heavens with noise, and yet, no scream is heard. The mystery of the unheard supernova waits just beyond the edge of dreams. The myth of the exploding star, that no one hears. A supernova shatters the dark with light, but not a single sound. If you stood beside it, your ears would strain for a roar that never comes. Yet, in its own way, the explosion does send tremors across the universe. You begin to listen with something deeper than your ears. Imagine this: that you float in the void, spacesuit humming softly, as a star prepares to die before your eyes. For weeks it has been growing brighter, swelling like a feverish heart against the black velvet of space. Now, in one impossible moment, it detonates with the energy of 100 billion suns. Light erupts in every direction, so intense it would vaporize you in an instant if you were truly there. Yet, silence. Complete, utter silence. The greatest explosion in the known universe happens without a whisper. No thunderclap. No shockwave you can hear. Just light streaming past your helmet in waves, illuminating your faceplate with colors no human language has names for. This is the paradox of the supernova, an event so powerful it can outshine entire galaxies, yet completely mute to our ears. Why? The answer takes us back to the nature of sound, that faithful traveler who refuses to cross the vacuum. When a star explodes, it does create pressure waves. Tremendous ones. The outer layers slam into interstellar gas at millions of miles per hour, creating ripples in the sparse medium between stars. But these ripples are so far apart, so weak compared to the vast emptiness they cross, that by the time they might reach something dense enough to hear them, they've faded to nothing. Yet to say a supernova is silent is perhaps the greatest trick our senses play on us. Because the universe records this violence in other ways. Close your eyes and imagine the aftermath, The explosion sends not just light, but a tsunami of subatomic particles, neutrinos, racing outward at nearly the speed of light. These ghostly particles pass through entire planets as if they weren't there, yet sensitive detectors on Earth can catch them. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino observatories registered a burst of 24 particles hours before the light arrived. Those neutrinos were the supernova's first whisper to the cosmos, a message sent through a medium far stranger than air. The dying star also leaves behind a pulsar in some cases, a rapidly spinning neutron star that beams radiation like a lighthouse. These beams sweep across space with such precise regularity that they might as well be the universe's metronome. The Crab pulsar, remnant of a supernova observed in 1054 AD, spins 30 times per second, its radio emissions creating a rhythmic pulse that, if converted to sound, would produce a tone near the lowest note on a piano. But perhaps most astonishing is how supernovas communicate through dust. The heavy elements forged in their cores, the iron in your blood, the calcium in your bones, are flung into space by the explosion. These atoms eventually find their way into molecular clouds, then new stars, then planets. In this sense, every supernova that ever was still speaks through the chemistry of our bodies. The carbon in your cells, the oxygen in your lungs, all were once part of stars that died in silence. This realization changes the meaning of listening itself. On Earth, we're accustomed to sound being ephemeral, a shout that fades, a note that decays. But cosmic sounds, these persist in different forms. The light that reaches our eyes from distant supernovas may have traveled for millions of years. The neutrinos passing through you right now could be ancient messengers from explosions that occurred before Earth formed. Even the gravitational waves from colliding neutron stars ripple through the universe long after the collision itself, warping spacetime like the fading vibrations of some colossal drum. As you drift deeper into these thoughts, consider this final paradox. The loudest events in the universe are silent, and yet their echoes last longer than any sound on Earth. That supernova whose light took centuries to reach us. Its story isn't over. Its remnants still expand into space, its pulsar, if it left one, still ticks with perfect rhythm, its heavy elements still journey through the cosmos. The explosion was merely the first syllable of a story that will continue for billions of years. And so you begin to understand. Silence isn't absence. It's a different kind of presence. As sleep draws nearer, your mind lingers on those silent tremors, the way a dying star's violence becomes the universe's whisper. And you wonder, if something as cataclysmic as a supernova can't make a sound, what hope does anything else have? Unless there are places where space itself becomes the instrument, where gravity plays notes no ear could ever hear. The hum of black holes, when space itself sings. Black holes do not scream, they resonate, bending spacetime like a drum. Their collisions send out gravitational waves, a music written in the fabric of reality. You imagine the universe as a vast, silent orchestra, playing notes we must translate. The cosmos is not silent, just speaking a different language. Imagine pressing your palm against the skin of a kettle drum. Now imagine that drum is the universe itself, not just the space between stars, but the very fabric of reality, stretched taut across creation. When two black holes spiral toward their final embrace, they don't create sound as we know it. Instead, they make the drum vibrate. These vibrations ripple outward at the speed of light, stretching and compressing spacetime itself as they pass. This is how black holes sing. Not with sound, but with gravity. The first time humanity heard this cosmic music was on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected a disturbance that lasted just 1/5 of a second, a barely perceptible wobble in the lasers of its massive detectors. When scientists converted the signal to sound, they heard something extraordinary, a quickening chirp, rising in pitch and intensity before suddenly cutting off. This was the death spiral of two black holes, one 36 times the mass of our Sun, the other 29, merging 1.3 billion light-years away. The sound is haunting when sped up to human hearing range, a soft whoop that starts at about 35 Hz, lower than the lowest note on a piano, and rises to 150 Hz before ending abruptly. That final moment is when the two black holes became one, when the last gravitational waves escaped before the new, merged black hole settled into silence. What's remarkable is how much this cosmic event resembles earthly music. The pattern follows what physicists call a chirp, a rapid increase in frequency that occurs as the black holes orbit faster and faster before merging. It's nature's version of a crescendo, building to a climax that shakes the universe. But how does empty space sing? The secret lies in Einstein's general theory of relativity, which predicts that massive accelerating objects should produce ripples in spacetime, gravitational waves. Think of these like the ripples on a pond, but instead of water moving up and down, spacetime itself stretches and squeezes. When two black holes orbit each other, they create a pattern of stretching and squeezing that radiates outward, carrying energy away and causing the black holes to spiral closer together. These waves aren't sound, but they share sound's fundamental nature, both are waves that carry energy through a medium. For sound, the medium is air or water. For gravitational waves, the medium is spacetime itself. The universe is full of such cosmic vibrations. Neutron stars, the dense remnants of dead stars, can spin hundreds of times per second, their slight imperfections creating continuous gravitational waves. Supermassive black holes at the centers of galaxies will eventually merge, producing deep rumbles that future detectors might hear. Even the Big Bang itself left behind a gravitational wave background, a faint hum from the birth of the cosmos. As you lie in the quiet of your room, consider this: right now, gravitational waves from distant cosmic collisions are passing through your body, stretching and compressing you by amounts smaller than an atom. The entire Earth is constantly being squeezed and stretched by these spacetime ripples. We simply lack the senses to notice. This realization changes everything. The cosmos isn't silent after all, we've just been listening for the wrong things. For centuries, we assumed the universe's soundtrack would come to us as sound waves in air. But nature is more imaginative than that. It composed its symphony in spacetime itself, using gravity as its instrument. And like any good symphony, the music contains secrets about its performers. From that brief whoop detected by LIGO, scientists could determine the black hole's masses, their distance from Earth, and even how fast they were spinning before merging. A single gravitational wave can tell us more about black holes than centuries of light-based astronomy. Perhaps most astonishing is the timescale. That merger happened 1.3 billion years ago, when Earth's most complex lifeforms were single-celled organisms. The gravitational waves have been traveling through an expanding universe ever since, finally reaching us now, at this precise moment in cosmic history. As sleep draws nearer, let your mind wander through this extraordinary idea, that right now, as you lie still, the fabric of reality itself is vibrating with message from the distant cosmos. The universe is alive with a music more profound than anything our ears could detect, a gravitational symphony playing on the grandest instrument of all. And as the darkness wraps around you, a final thought lingers: if black holes can make spacetime sing, what other cosmic instruments might be playing their parts in this grand orchestra? Perhaps closer to home, our own sun, that golden disk in the daytime sky, has been humming its own quiet tune all along. The sun's secret vibrations, a lullaby of plasma. Our star does not crackle like a fire, it pulses, a slow, deep heartbeat. Helioseismology listens to the sun's hidden song, its surface rippling like water. You picture these waves as the sun's way of breathing, of sighing. And somehow, it soothes you to know even a star trembles. Breathe in. Breathe out. Now imagine that same rhythm stretched across 864,000 miles of churning plasma, a star taking one slow, celestial breath every 5 minutes. This is the hidden pulse of our sun, a vibration so vast it would take 20 Earths lined up to cross just one of its ripples. For centuries, we thought of the sun as a silent orb, a brilliant but motionless light in the sky. Then in 1960, astronomers made an astonishing discovery: the sun's surface isn't still at all. It shimmers like the skin of a drum, rising and falling in regular patterns. The entire star breathes in and out with oscillations that, if translated to sound, would create deep, resonant tones far below human hearing. This is helioseismology, the study of the sun's vibrations, and it reveals our star as a complex, singing sphere. Close your eyes and picture the sun's surface. Not the smooth yellow disk we see from Earth, but a seething ocean of plasma, its waves cresting at heights greater than Mount Everest and moving at speeds that would cross the Atlantic in minutes. These aren't true waves like those in water, but something more profound: pressure waves created by turbulent convection deep within the star. Hot plasma rises from the interior, cools at the surface, and sinks back down in a continuous cycle, a process that takes about 1 million years for a single plasma particle to complete. These movements create distinct vibrational patterns called modes. The sun's P modes, pressure modes, are like spherical versions of a bell's ringing tones, sound waves trapped inside the star, refracting back and forth between the surface and interior. The lowest frequencies have wavelengths so large they wrap around the entire sun, while higher frequencies create intricate interference patterns across its surface. If we could hear these vibrations at their true pitch, the sun would sing a chord spanning many octaves, with the deepest notes around 0.003 Hz, one vibration every 5 minutes, and higher harmonics reaching up to 5 Hz, shift these frequencies up 42 octaves to make them audible, and the sun's voice emerges as a haunting, resonant hum, the sound of a star tuning itself. But why does this matter? These vibrations aren't just celestial music, they're our only way to see inside the sun. Just as geologists use earthquakes to probe Earth's interior, solar physicists use these oscillations to map the sun's hidden structure. The vibrations reveal internal rotation rates, temperature variations, even the motion of plasma currents deep beneath the surface. One remarkable discovery came when scientists noticed certain vibrations arriving slightly earlier than predicted. This revealed the sun's tachocline, a thin, turbulent layer where the star's rigidly rotating core meets its differentially rotating outer layers. It's like finding a hidden chamber in a musical instrument by studying how its sound changes. The sun's vibrations also connect to its magnetic personality. During solar maximum, when sunspots pepper the surface, the sun's entire acoustic spectrum changes. Certain frequencies become more prominent, others fade, as if the star were changing key in response to its own internal dynamo. Sometimes, massive solar flares trigger starquakes that send ripples across the surface like a stone dropped in a pond. As you lie in bed, imagine. Right now, sunlight warming your skin carries encoded messages about these vibrations. Each photon began its journey in the sun's core up to 1 million years ago, then bounced randomly through the radiative zone before finally emerging, a process that imprinted the sun's acoustic signature on the light itself. There's poetry in this realization. The sun, which seems so constant from our earthly perspective, is actually a dynamic, vibrating being. Its steady light is the product of endless internal motion, a balancing act between gravity's inward pull and the outward pressure of nuclear fusion. The very constancy we depend on emerges from ceaseless fluctuation. Perhaps this is why the sun's hidden vibrations feel so soothing to contemplate. They remind us that stability and motion aren't opposites, that even something as apparently steady as our star pulses with quiet rhythms. The sun doesn't just shine, it breathes. It doesn't just exist, it resonates. And in that resonance, we find an unexpected connection. The calcium in your bones, the iron in your blood, these elements were forged in ancient stars that pulsed with their own vibrations before exploding to scatter their material across space. The rhythm of the cosmos echoes in your veins. As sleep pulls at your eyelids, the sun's silent song lingers in your mind, a reminder that even the most familiar lights can hold hidden depths. And you wonder, if our own star hums with such secret vibrations, what songs might the planets be singing? Their voices, you suspect, would be stranger still, not the warm tones of plasma, but the eerie whispers of magnetic fields and charged particles dancing in the solar wind. The radio whisper of the planets, turning light into sound. Jupiter's auroras crackle like distant static, Saturn's rings hum in radio waves. Scientists take these signals and transpose them, letting planets sing in our voices. You close your eyes and imagine each world as an instrument in a grand, silent choir. What would Earth sound like, if someone out there was listening? Imagine holding a seashell to your ear, that hollow roar we childhood pretend is the ocean. Now imagine that shell could pick up transmissions from worlds millions of miles away. Not voices, not music, but something far stranger, the natural radio emissions of planets, converted into sounds our ears can understand. This is how we hear the solar system. Jupiter speaks first, its voice a haunting series of clicks and pops that sound almost artificial. These are Jovian kilometric radiation emissions, created by charged particles spiraling along the gas giant's powerful magnetic field lines. When NASA's Juno spacecraft recorded these signals and shifted them into the audible range, the result was something between static and whale song, a reminder that the largest planet in our solar system is essentially a massive electrical generator, its magnetosphere extending so far it would appear 2 to 3 times larger than the full moon in Earth's sky if our eyes could see radio waves. Saturn sings differently. Its rings, those breathtaking bands of ice and dust, generate radio emissions as they interact with the planet's magnetic field and the solar wind. The Cassini spacecraft detected these signals and scientists translated them into sound, producing eerie tones that rise and fall like a theremin in an old science fiction film. The pitches correspond to dust particle density. The more material a ring contains, the richer its radio voice becomes. But the true virtuoso of planetary radio might be Io, Jupiter's volcanic moon. As it orbits through Jupiter's magnetosphere, Io acts like a cosmic power generator, creating million-amp electrical currents that flow along magnetic field lines to Jupiter's poles. These currents produce radio emissions so powerful they were detected by Earth-based radio telescopes before any spacecraft visited Jupiter. The resulting sounds, called Io-controlled decametric emissions, resemble laser blasts from a 1950s space opera, sharp, staccato bursts that come and go as the moon moves in its orbit. These aren't true sounds, of course. They're electromagnetic vibrations shifted into our hearing range, like taking a painting and translating its colors into music. But the process reveals something profound. Each planet has its own distinct voice determined by its magnetic personality. Earth sings too. Our planet's magnetosphere generates its own chorus of radio emissions, whistling tones caused by plasma waves moving along magnetic field lines. These chorus waves sound like birds chirping at dawn, if those birds were made of ionized gas and singing in the vacuum of space. Astronauts on the International Space Station sometimes hear them as unexpected static in their headsets, the literal sound of Earth's magnetic field interacting with the solar wind. As you lie in the quiet dark, consider this: right now, these planetary transmissions are passing through your room. Jupiter's radio bursts, Saturn's ring tones, Earth's magnetic chorus, all exist as invisible vibrations in the electromagnetic spectrum, waiting for our technology to translate them into something our limited senses can perceive. The process of converting these signals teaches us something fundamental about listening. On Earth, sound requires molecules to bump against each other. But across interplanetary space, information travels just fine as electromagnetic waves, whether as visible light, radio static, or the plasma oscillations that create those haunting chorus emissions. The universe doesn't care about our biological limitations, it communicates in whatever medium is available. Perhaps most moving is how these translated planetary voices connect us to worlds we'll never visit. That crackling from Jupiter? It's the sound of charged particles raining down on the gas giant's polar regions, creating auroras that would dwarf our entire planet. Saturn's eerie tones. The music of countless ice particles, each no larger than a snowball, shepherded into intricate patterns by the gravity of tiny moons. Even Earth's chorus waves tell a story, of our protective magnetic bubble constantly negotiating with the solar wind, deflecting radiation that would otherwise strip away our atmosphere. As sleep draws nearer, let your imagination wander further. If an alien civilization pointed their radio telescopes at our solar system, what would they hear? Not the content of our broadcasts, those grow fainter with distance, but the natural radio voices of our planets, each world contributing its unique tone to a symphony lasting billions of years. They might notice how Earth's emissions changed with the advent of electrical technology, or how Jupiter's storms create temporary shifts in its radio signature. And perhaps, just perhaps, they'd wonder, as you do now, whether someone on a pale blue dot was listening back. The thought lingers as consciousness fades: if planets can speak across the void in radio whispers, what older messages might the universe carry? Somewhere in the crackling static of the cosmos, there may exist a far more ancient signal, an echo from when space itself was young, when the first vibrations rippled through a newborn universe. The echo of the Big Bang, a faint memory of sound. In the beginning, the universe was dense enough to carry sound waves. The cosmic microwave background holds their ghostly imprint, a fading lullaby. You think of it as the first and last sound, a whisper from time's dawn. And in that echo, everything began. Picture the universe in its infancy, not the vast, yawning expanse we know today, but a hot, dense plasma so compressed that light could barely travel before being absorbed again. In these first moments after the Big Bang, space wasn't empty. It was a seething ocean of particles where sound waves could propagate, not through air, but through the quark-gluon plasma that filled all existence. This primordial medium carried vibrations unlike any sound we know. The early universe's sound waves weren't pressure waves moving through molecules, but actual ripples in spacetime itself, dense regions compressing and expanding as gravity fought against the outward pressure of radiation. These cosmic sound waves traveled at nearly two-thirds the speed of light, their wavelength stretching across hundreds of thousands of light-years as the universe expanded. Then, 380,000 years after the Big Bang, something extraordinary happened. The universe cooled enough for electrons and protons to combine into hydrogen atoms, an event called recombination. Suddenly, light could travel freely for the first time. That flash of liberation is what we now detect as the cosmic microwave background, CMB, the oldest light in the universe, carrying with it the frozen imprint of those primordial sound waves. When you look at a CMB map, you're seeing sound waves fossilized in light. The hot, red, and cold, blue, spots form a pattern of peaks and troughs that reveal the universe's acoustic signature at the moment of recombination. It's as if someone took a snapshot of a vibrating bell just as it was struck. The CMB shows us the universe ringing at precise, predictable frequencies. Scientists call this pattern baryon acoustic oscillations. The term sounds complex, but the concept is beautiful in its simplicity. Matter, baryons, clumped where sound waves compressed plasma, creating a characteristic spacing between galaxies that persists to this day. The very large-scale structure of the universe, the great cosmic web of galaxy clusters and voids, bears the imprint of these ancient vibrations. If we could hear these primordial sounds at their original frequencies, they would be far too low for human ears, about 50 octaves below the threshold of hearing. But when shifted up into our audible range, the universe's first sounds resemble a deep, resonant hum, like the aftermath of some colossal gong struck at the dawn time. This cosmic soundtrack reveals astonishing details about our universe's birth. The precise spacing of the CMB's hot and cold spots tells us the universe is flat to within 0.25% margin of error. The relative heights of the acoustic peaks reveal that ordinary matter makes up only about 5% of the universe's content, with dark matter and dark energy constituting the rest. Even the slight polarization patterns in the CMB, called B-modes, may carry evidence of gravitational waves from cosmic inflation, the universe's exponential expansion in the first fraction of a second after the Big Bang. As you lie in the quiet dark, consider this: the pillow beneath your head contains atoms forged in those primordial sound waves. The hydrogen in your body is the same hydrogen that formed when the universe became transparent, the same hydrogen that once carried those vibrations across the infant cosmos. You are, quite literally, made from the echoes of creation. The most profound realization comes when you trace these sound waves backward. The patterns we see in the CMB weren't random fluctuations, they were quantum mechanical vibrations from the universe's first moments, stretched across cosmic distances by inflation. Those microscopic quantum jitters became the seeds for all structure in the universe. The galaxies, stars, and planets exist because of sound waves that began as quantum noise in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. This means the universe's first sounds weren't just a side effect of its birth, they determined its very shape and destiny. The cosmic symphony didn't accompany creation, it was creation. The vibrations were the blueprint. Now, 13.8 billion years later, those sound waves have faded into near silence. The universe has expanded so much that new sound waves can no longer propagate through the diffuse intergalactic medium. The CMB is growing fainter as the universe expands, its photons stretching into longer wavelengths. In another trillion years, the CMB may be undetectable altogether, the universe's first and last sound finally fading beyond even our most sensitive instruments' ability to hear. But for now, the echo remains. Specialized telescopes like the Planck satellite continue mapping the CMB's subtle variations, while experiments like BICEP and the Simons Observatory search for the telltale signs of primordial gravitational waves in its polarization patterns. Each new measurement adds another note to our understanding of the cosmic symphony. As sleep draws nearer, let your mind drift back to those first moments. The entire universe vibrating like a drumhead, its frequencies determining where galaxies would one day form. The sound waves that shaped existence itself. And the remarkable truth that we, products of those ancient vibrations, have developed the ability to listen back through time, to hear the fading whisper of creation. The thought lingers as consciousness wanes: if the universe's birth left such profound vibrations, what other cosmic notes might still resonate through the void? Somewhere between the fading echo of creation and the present moment, there may exist another sound, one so deep, so vast, it took the collision of black holes to make it audible. The sound we almost heard, when space nearly spoke. In 2003, a black hole sent out the lowest note ever detected, a B-flat 57 octaves below middle C. Too deep for human ears, it reverberated for millions of years. You wonder, if sound could travel freely, would space be a cacophony or a chorus? Perhaps silence is a gift, after all. There exists a note so deep it defies imagination. In 2003, astronomers studying the Perseus galaxy cluster detected pressure waves rippling through the superheated gas surrounding its central black hole. These waves, spaced hundreds of thousands of light-years apart, corresponded to a musical note 57 octaves below middle C, a B-flat that would vibrate once every 9.6 million years if played at. This is the deepest note ever discovered in nature. To comprehend such a sound, imagine slowing a grand piano's lowest note until each vibration lasts longer than human civilization. The wavelength stretches farther than the distance between Earth and the Large Magellanic Cloud. It is less a tone than a geological event, a seismic shift in the fabric of intergalactic space. And yet, mathematically, it qualifies as sound, a periodic compression wave moving through a medium, in this case the thin plasma filling the galaxy cluster. The Perseus black hole didn't produce this note continuously. Astronomers believe it resulted from periodic bursts of energy as the black hole consumed matter, each meal creating a pulse that sent spherical pressure waves expanding through the cluster's gas like ripples from a stone dropped in a pond. The Chandra X-ray Observatory detected these ripples as subtle variations in X-ray emissions, regions slightly hotter where the gas was compressed, slightly cooler where it expanded. What's astonishing isn't just the note's depth, but its endurance. These waves have been propagating for about 2.5 billion years, since before multicellular life existed on Earth. They will continue ringing for hundreds of millions of years more, gradually fading as their energy dissipates into the cluster. This is sound as a cosmic phenomenon, operating on timescales that dwarf human history. Yet here's the paradox: we could never actually hear this note, even if we were floating in the Perseus cluster. The gas is so diffuse that the pressure changes would be imperceptible to human senses, about 1 part in 10,000 of Earth's atmospheric pressure. Our ears evolved to detect pressure waves in air, not the barely there undulations of intergalactic plasma. This raises a profound question: if we could hear all the vibrations occurring in space, from the sun's oscillations to black hole tones to the cosmic microwave background, what would the universe sound like? The answer depends on where you listen. Near a young, massive star, you might hear a constant roar of supersonic stellar winds colliding with interstellar gas. In the accretion disk around a neutron star, plasma spiraling inward at nearly light speed could create a screaming crescendo of X-ray frequencies. The solar wind interacting with Earth's magnetosphere produces ultra-low frequency, Whistler waves, that sound like falling tones when converted to audio. But step back to intergalactic space, and the picture changes. The average density of the universe is about 1 atom per cubic meter, far too sparse for traditional sound waves. Any vibrations would be so attenuated they'd register more as subtle temperature fluctuations than audible tones. The dominant sound might be the occasional gravitational wave from colliding black holes, a brief chirp every few minutes across the entire observable universe. Perhaps the universe's silence isn't an absence, but a carefully balanced composition. The sparse medium prevents sound from traveling far, creating natural isolation between cosmic events. Without this acoustic insulation, space might be an overwhelming cacophony, the combined noise of every star, black hole, and plasma shockwave drowning out all individual meaning. Instead, We get curated signals, the occasional gravitational wave chirp, the rare converted radio emission, the fossilized sound waves in the CMB. There's wisdom in this design. Just as Earth's atmosphere filters harsh solar radiation while allowing visible light to pass, the universe's acoustic properties filter noise while permitting specific vibrations to reach us, whether as light, gravitational waves, or the subtle X-ray variations that revealed the Perseus black hole's deep note. As you drift towards sleep, consider this final thought, that B-flat 57 octaves below middle C is still ringing right now. The pressure waves continue expanding through the Perseus cluster, their wavelength so vast it would take a spaceship moving at light speed 300,000 years to travel from one crest to the next. The sound will outlast our sun, our galaxy, perhaps even the local group of galaxies. And somewhere, in some distant future, another civilization's astronomers may detect its faint echo, a reminder that even the quietest universe still sings, if you know how to listen. The darkness wraps around you like the sparse plasma between galaxies, and a final thought surfaces: if the cosmos contains notes too deep for ears and vibrations too subtle for touch, how many other messages are we missing? What might we hear if we learned to listen with something beyond our biology, to translate the universe's full spectrum of whispers? Listening without ears, how we hear the universe. Telescopes are ears for light, radio dishes catch whispers we cannot. You realize we are always translating the cosmos, turning its language into ours. The universe does not need sound to tell its story, but we need stories to understand it. And so, you listen, in your own way. You stand barefoot on cool grass, head tilted back as the Milky Way spills across the night sky. The scene is utterly silent, no cosmic hum, no interstellar winds rushing past your ears. Yet you know, with absolute certainty, that you are surrounded by voices. Every photon striking your retina is a messenger. The blue-white glare of Vega carries information about its scorching surface. The reddish glow of Betelgeuse whispers of its impending supernova. Even the dark spaces between stars speak, their very blackness telling of light absorbed by interstellar dust or stretched by the expansion of the universe. This is how humanity listens to the cosmos, by translating light into understanding. Consider the humble radio telescope, its parabolic dish collecting electromagnetic waves just millimeters to meters long. When Jocelyn Bell detected the first pulsar in 1967, she wasn't hearing actual sound but seeing rhythmic pulses on a chart recorder. Yet astronomers soon realized these signals, when converted to audio, produced precise ticks like a cosmic metronome. The translation revealed their nature, spinning neutron stars beaming radiation like lighthouse beams. Modern telescopes take this further. The Event Horizon Telescope's image of the M87 black hole's shadow wasn't captured in visible light but assembled from radio wave data, a translation of information our eyes couldn't perceive into an image our brains could comprehend. Similarly, X-ray telescopes like Chandra convert high-energy photons into false-color images, letting us see the million-degree gas swirling around black holes. But the most profound translations happen inside supercomputers. When LIGO detects gravitational waves, the signal is often weaker than the quantum noise in its lasers. Only by comparing the data against millions of simulated black hole collisions can scientists extract the faint chirp. This isn't just listening, it's collaborative storytelling between human intuition and machine learning. The artistry of these translations becomes clear when you compare how different instruments render the same phenomenon. Saturn's radio emissions sound like eerie whistles when processed one way, like crashing waves when processed another. The solar wind's interaction with Earth's magnetosphere can resemble birdsong or static depending on which frequencies scientists emphasize. These variations aren't deceits but different dialects, ways of making the inaudible comprehensible to our limited senses. Perhaps the most moving translations are those that engage multiple senses simultaneously. Sonification projects like NASA's Black Hole Echoes combine X-ray data with musical tones, allowing listeners to experience light echoes from black hole flares as rising and falling pitches. The pillars of creation have been rendered not just as visible light Hubble images but as tactile 3D prints audio representations where vertical position correspond. These experiments reveal an essential truth: the universe communicates through any medium available. Just as water can exist as ice, liquid, or vapor while remaining H2O, cosmic information manifests as light, gravitational waves, or particles while telling the same underlying story. Our challenge isn't that the universe is silent, it's that we're monolingual in a cosmos that speaks every language. As you lie in bed, consider how your own body performs similar translations every moment. Your inner ear converts air pressure waves into electrical signals your brain interprets as sound. Your retina translates photons into neural impulses perceived as color and shape. In this sense, you are already a walking telescope, a biological instrument tuned to a narrow slice of reality's spectrum. The great leap of astronomy has been extending these natural capacities. Just as a microscope reveals unseen worlds in a drop of water, our telescopes unveil cosmic processes hidden to unaided senses. The colors in a nebula photo may be false, but the physics they represent is profoundly real: stellar nurseries where new suns ignite, shock waves from ancient explosions, magnetic fields sculpting gas into intricate shapes. This translation work continues beyond professional astronomy. When you look at a star map app on your phone, algorithms are converting satellite data into real-time constellations. When astronauts describe seeing Earth's thin atmosphere from orbit and feeling overwhelmed by its fragility, they're translating visual input into emotional understanding. Even children connecting dots to form Orion are participating in humanity's oldest practice, turning cosmic patterns into stories. The night grows deeper. Your breathing slows. And in this twilight state between waking and dreaming, you realize something profound: the universe doesn't care whether we perceive it accurately. Supernovas will explode whether we see them or not. Black holes will merge whether we detect their gravitational waves or not. Reality exists independent of observers. But we, curious, storytelling creatures, can't help but try to understand. So we build instruments to extend our senses. We create metaphors to bridge the gap between quantum mechanics and intuition. We compose symphonies from radio static and paint galaxies with invisible light. Not because the universe demands it, but because we do. As sleep finally claims you, a final thought lingers like starlight in morning's approach: perhaps the most beautiful translation isn't from cosmic data to human senses, but from knowledge to wonder. For in the quiet between the notes, in the darkness between the stars, that's where the deepest understanding lies, not in what we hear, but in how we listen. Last chapter, the quiet that connects us, a universe of shared silence. You lie still, feeling the hush of space wrap around you like a blanket. In the absence of sound, there is a different kind of music, one of wonder, of awe. The quiet truth is this: space sings, just not in a way we can hear. And as you drift to sleep, you realize, silence is its own kind of song. Breathe in. Breathe out. Notice how the air moves through you, how your ribs expand to make room for the atmosphere that sustains you. This simple act connects you to every living thing on Earth, to the trees exchanging gases with the sky, to the whales breaching through ocean surfaces to take their own deep gulps of air. But it also connects you to something far greater: the cosmic dance of matter and energy that make such breaths possible. The oxygen in your lungs was forged in stellar furnaces. The carbon in your cells was scattered across interstellar space by dying stars. Even the hydrogen in your body's water molecules dates back to the primordial universe, a relic of creation itself. These elements traveled soundlessly through the void for eons before becoming part of you. This is the paradox we've explored together: space appears silent not because nothing is happening, but because its vibrations exist beyond our narrow biological perception. The universe thrums with activity, particles accelerated to near light speed, magnetic fields twisting plasma into intricate shapes, spacetime itself rippling from cataclysmic events. We've learned to translate some of these phenomena into forms we can understand, converting radio emissions to sound, gravitational waves to chirps, cosmic background fluctuations to temperature maps. But tonight, as sleep draws near, consider embracing the silence not as absence but as invitation. The quiet of space is what allows us to distinguish signal from noise, to pick out individual cosmic events from what would otherwise be an overwhelming cacophony. Just as the dark between stars makes their light visible, the silence between vibrations gives them meaning. That 9.6 million year B-flat from the Perseus cluster matters precisely because we can isolate it from the background. The gravitational wave chirp of colliding black holes tells its story because it stands out against spacetime's calm. There's wisdom in this cosmic quiet. On Earth, we're surrounded by constant noise, traffic, devices, the hum of electrical infrastructure. Our soundscapes rarely dip below 30 decibels, even at night. But the universe, for all its violence and grandeur, maintains an essential hush across most of its volume. This isn't an accident of physics but a consequence. Sound requires proximity, matter, connection. The silence of space is the silence of distance, of the incredible rarity of particles bumping against one another across light years. Yet this very silence connects us in unexpected ways. When astronauts float aboard the International Space Station, one observation always strikes them: from orbit, there are no borders visible on Earth. The planet presents itself as a whole, fragile biosphere. That perspective, often called the overview effect, emerges from seeing our world against the silent blackness. You don't need to leave Earth to experience this. Step outside on a clear night, away from city lights. Let your eyes adjust until the Milky Way emerges. Notice how the silence, no birds, no wind, just your own breath, makes the stars feel closer. That's not an illusion but a different kind of truth. In the absence of earthly distractions, your mind can finally resonate with deeper realities. Scientists are beginning to understand how profoundly silence affects our brains. MRI studies show that periods of quiet stimulate hippocampus growth, the region associated with memory and emotion. Other research suggests silence helps brain cells regenerate and improve sleep quality. Perhaps this explains why we instinctively seek quiet places for contemplation, why libraries and cathedrals and meditation gardens cultivate stillness. We're drawn to silence because, on some level, we recognize it as our cosmic birthright. The universe began in fire but expanded into calm. The same physics that prevents sound from traveling through interstellar space also gave us the quiet necessary to develop technology, art, philosophy. Imagine if space conducted sound like water: every supernova blast, every asteroid impact, every solar flare arriving as deafening noise. Civilization might never have emerged under such cacophony. As your breathing slows further, think of all the ways silence serves life. It allows bats to distinguish their returning echoes from background noise. Lets whales communicate across ocean basins with low-frequency calls. Gives owls the ability to locate prey by the faintest rustle. Permits scientists to detect exoplanets through tiny stellar wobbles. The pattern is clear: silence isn't emptiness but the blank page on which meaningful signals write themselves. Now turn this insight inward. The quiet moments before sleep, when today's worries fade and tomorrow's plans haven't yet formed, are when your mind does its most important work. Memories consolidate. Creativity stirs. The subconscious sorts through experiences, deciding what to keep and what to release. This mental silence is as vital as the cosmic variety. You're floating now, not in space but in that liminal state between wakefulness and dreams. The boundaries feel porous, as if you might dissolve into the quiet surrounding you. Let go. There's no need to grasp for understanding tonight. The universe will continue its silent operations whether you comprehend them or not: stars fusing hydrogen, galaxies spinning, quantum fluctuations sparking virtual particles into momentary existence. What remains is simple awareness: the rise and fall of your chest, the weight of blankets, the faint pulse at your wrist or throat. These tiny vibrations, your personal contribution to the universe's grand vibration spectrum, connect you to everything we've explored. The sun's 5-minute oscillations. Jupiter's radio whispers. The CMB's fossilized sound waves. Black holes' gravitational chirps. You are, in this moment, both observer and participant, a conscious node in the cosmic web, contemplating the silence that makes all connections possible. Story closing line. And so we find, in the quiet between the stars, a truth both simple and profound. The universe sings, not in sound, but in light, in gravity, in the language of motion itself. We are its listeners, learning to hear with more than just our ears. As you drift into dreams tonight, remember, you are part of this cosmic symphony, vibrating to rhythms older than time. Do not subscribe our channel, laugh, good night, and sleep well beneath the silent music of the spheres.